So in this lecture, we're going to discuss the second piece of evidence for the quantum theory of light. That is to say, the second piece of evidence for the fact that light exists in the form of particles, quantized particles. That piece of evidence is Einstein's photoelectric effect. He won the Nobel Prize for this discovery. So when light strikes the surface of a metal, what happens? Okay, so if we have light, you can think of it as a stream of photons hitting the surface of a metal, electrons get emitted from that metal. Okay, so we can sum up the photoelectric effect by saying that electrons get emitted from the surface of a metal when light strikes it. When light strikes it. So we can look at the mass and velocity of the electrons that get emitted to figure out how energetic the photons are. So what you can find is that the kinetic energy, I'm going to abbreviate kinetic energy as KE. Kinetic energy is the energy of motion. So the electrons that get emitted from the surface of the metal are traveling very fast. And you may have seen this equation for kinetic energy before. Don't worry if you haven't. That kinetic energy equals 1/2 mv squared. The m and the v here refer to the mass and velocity of the electron that gets emitted. Now, you can look up the mass of an electron. Its velocity can be measured. And the interesting thing with the photoelectric effect is that that kinetic energy is related to the energy of the incident photons, so the energy of the photons that hit the surface of the metal. And we have to subtract a certain threshold energy. Okay, so let me define what each of these terms is in this equation. This is the energy of, hang on, let me make that a bit smaller, the incident photons. So the particle of light that strikes the surface of the metal. The second term here is the threshold energy. So the threshold energy is the minimum amount of energy required to eject an electron. So this is kind of related to a famous equation that you have probably seen before, Einstein's famous relationship relating energy to mass and the speed of light, E equals mc squared. I think most everybody has seen that equation. So this equation, like the equation above it, is just saying that energy is equal to mass times the velocity squared. Here we're just talking about speed of light in the place of velocity. Let's rearrange this equation for a second to solve for mass. So mass is energy over speed of light squared. And if you recall from the previous lecture, we can define energy as hc over wavelength, where h is Planck's constant, c is the speed of light, and lambda is the wavelength of the light that we're talking about. So I can plug that in here, hc over lambda, for energy, and then I still have c squared in the bottom. Now I can cancel one of those c's, so this simplifies to h over lambda times c. Okay, and again, this is equal to the mass of the particle that we're talking about, in this case, the electron. Let's rearrange this to solve for the wavelength. So the wavelength lambda is equal to Planck's constant over the mass times the speed of light. Now, I'm going to simplify this by just calling the speed of light v for velocity. And this is kind of a useful form of this equation, which is called the de Broglie wave equation. And it's a beautiful equation that kind of quantitatively expresses the wave-particle duality. What this equation does is it relates wavelength, which is a wave property, to the mass and velocity of a particle. Okay, so you can have a particle with mass m and velocity v, and you can calculate its wavelength using Planck's constant. So this is a really beautiful unification of the wave-like and particle-like properties of light.